Hey, welcome guys. This is Mr. Sheeline. If you're watching this video, that means that you are watching the notes for the Unit 2.1 notes covering atomic structure, okay? Okay. So this is for the most part, or what should a decent chunk of this should be, is it should be review, and it should be expanding upon things we already know, and also maybe kind of working with things that we haven't worked with in a long time. One of those things being the periodic table. So let's just get right into it. Okay, so the atom. Here I'm going to, actually I got to keep that. So the atom. All right. Still haven't figured out the best way to do all this. But anyway, so the atom. The atom, as we remember, the atom is the smallest particle of an element that retains the chemical identity of said element. Okay, so this is the, for the most part, it's the smallest piece of matter. Again, for the most part, it's the smallest piece of matter that we've been able to somewhat observe. Okay, there are there are images that we do have, some very, very complicated images that scientists have been able to put together, that show an accurate representation of what an atom looks like. But obviously, we can't exactly pick it up off a table and look at it and observe it up close. Okay, that's why we use models. That's why we use the photographs in order to make models and see that. But anyway, but we should remember this: it's the smallest particle in an element. Okay. All right. Sorry, excuse me. All right, so the chemical symbol. Let's see, make sure. Yeah. Now the chemical symbol. This is your abbreviation of an element found in the periodic table. So I wanted to recap this because we're going to be creating what's called a complete chemical symbol. Okay, so those abbreviations that you see, so like, for instance, hydrogen has an H, oxygen has an O, helium has HE. All of those abbreviations, that is a chemical symbol. Okay, and I should have, yeah, I've got some conditions. So there are some conditions that come along with these symbols. So remember, the first letter of a chemical symbol is always, 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 always capitalized. Okay? It's always capitalized because this is how we distinguish one. This is how we distinguish one element from another. Because you could imagine that if an element had two letters and both of them were capitalized, it would make it super difficult to understand which one is which. So our first letter is always capitalized, and then if it has a second letter, it is always, 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 always lowercase. And again, that's if it has one. Okay, a good chunk of them do have second letters. A good chunk of them don't. So as an example, like I said, it's like H is for hydrogen, Al is for aluminum, and then Ca is for calcium. Okay. Now notice how the C is capitalized and the A is capitalized. The A is capitalized for aluminum. The L is lowercase for aluminum. Well, hydrogen just has the H all by itself. So when we are working with chemical symbols, it is important to remember that we use uppercase and lowercase letters, and you have to know which one is which. You have to know that the first letter is always capitalized, and then the second letter is always lowercase. Okay, we have to know this. We've got to remember this. Okay, we've got to remember it. Because when we are writing this, when we are balancing equations, when we are writing out chemical equations, when we are doing Stoic, whatever it is that we are doing, we have to make sure we're properly writing these in, because if you do write, say, a capital A and then capital L, no matter what it is, it's going to be wrong. Okay, if you put capital C and then capital A, that's going to be wrong 100% of the time in my class. So we have to make sure that when we are looking at a periodic table, when we are writing down the particular chemical symbol for a particular element, you have to have the correct organization. You have to have the correct symbol. Okay, super duper important to remember and to follow through with. All right, so the atomic number. Okay, so the atomic number So you see here, the atomic number is the number equal to the number of protons in an element. Okay, so the atomic number is, and we'll get to this in a bit, but it's the number equal to the number of protons in an element. Okay, so as a couple examples, sorry. So aluminum's atomic number is 13, which means that aluminum has 13 protons. Calcium's atomic number is 20, which means calcium has 20 protons. Okay, now I'm going to go through atomic mass, and then I'm going to talk about where we can find these guys, because I'm sure you're like, well, Mr. Sheeline, where'd you get the 13? Where'd you get the 20 for aluminum and calcium, respectively? I'll get to that after we talk about atomic mass, because they're both found in the same on the same thing. Okay, more or less, and I'll detail that in a second. Okay, so again, atomic number. This is how many protons an element has. But then there's the atomic mass. So the atomic mass is going to be the average mass of all of the naturally occurring isotopes of an element. Okay, well, what's an isotope? Well, we'll get to that in a second, but just understand this is the average mass. The average mass of naturally occurring isotopes in of an element, sorry. All you have to know for right now is that each kind of element has a different type of itself. And we find the atomic mass by seeing what the abundance of a particular type of an element is in the natural world. And we take that, and we take what its the mass of that particular element, that atom of an element or molecule, or actually, atom, we take that, and for the most part, we divide it against the abundance of the other type of that particular element, and then find its natural or its atomic mass. We don't get into too much detail in that, but we will have a lab later on this week detailing this. But for now, this is enough. So anyway, so here are some examples. Now, these two numbers, however, just understand these two numbers are just for the purposes as an example on this on the notes. I'll detail later on, and as we go along, that we need to go by a certain number of decimal points, because the materials you'll have that you'll be able to use on quizzes and tests will have a specific atomic mass associated to each element that is not this long. They're a bit shorter. Okay, so just keep that in mind. Okay, so as an example, aluminum's atomic mass is 26.98154, which is a decently precise measurement. Calcium's is 40.078. Okay. Okay, now you can ask me, Mr. Sheeline, where can we find that kind of information? How do we know that aluminum's atomic number is 13? I'm so glad that you asked, amazing student. So where we find this information is, if you haven't already guessed, and I'm sure some of you have, where we find that information is in the periodic table. Okay. Now, some periodic tables are arranged a little bit differently. So, of course, it has the same classic structure, like as in, how the elements are arranged. It pretty much doesn't change. But what does change is how the information about each element, that can change. So, for instance, the one that I have here in my room, if you look at, let's say we look at aluminum, okay, aluminum will have its chemical symbol. Oh, come on. Geez. It'll have its chemical symbol. Sorry, my stylus is not having it today. Okay. Here, I'm going to try that again. It'll have its chemical symbol here. Okay. There we go. Yeesh. So it'll have its chemical symbol, and then it'll have some other things. Mine, for instance, mine does, I believe, detail the different isotopes for each element, and I think it also does provide information for its orbitals, which we hopefully will be able to get to at the end of the year here, orbitals. But nothing we need to know terribly right now. But what it does have, other than that material, something that we've already discussed, it will have your atomic mass and your atomic number. Okay, and it's important that we don't mix these up. So a good way to remember, the difference between the two is that your atomic mass here, atomic number, this is always going to be a whole number. Oh my goodness, my stylus. This is going to be a whole number. Okay. While the atomic mass here is going to be a decimal. It's going to be a fraction. Okay. So when you look up at a periodic table, what you'll see is that you'll see each box with its chemical symbol in it, and typically two numbers. So for aluminum, it's going to have this is on my periodic table that's there on the wall in my classroom. It has a 13 in the corner. So when we look at that 13, we should say, okay, that's a whole number. So because it's a whole number, I don't think that can be my atomic mass. And so if you see that, you'd think to yourself, okay, if it's not atomic mass, then I think that should be my atomic number. And you'd be right. 13 is aluminum's atomic number. And what that tells us is that aluminum has 13 protons in the nucleus of the atom. Okay, so remember, there'll be a small review, but just as a reminder, remember the nucleus of an atom. You can Google it real quick. It's more or less just the center of the atom where the neutrons and the protons sit, with the electrons on the outside in the cloud. So anyway, so there's 13 protons in aluminum. So, and then on my and I can't read it from here sitting on my demo desk, but I can see it's like a decently long decimal. But here at the top is where you'll find your atomic mass. And I'm just going to put in what I've got here in the notes. So it'd be like not 29, but 26.98154. Okay. So again, the reason why I'm drawing this is because sometimes you have the chemical symbols on a periodic table and their information arranged differently. So this one is in my room. Okay. Now, but what you may see on other, maybe websites, you may see in other periodic tables, it may be arranged like this. This one I see a lot often is that there we go, Mr. Penn. So I'll see, if we're still sticking with aluminum, a lot of times I'll see the atomic mass on the very bottom. It'll be like this. Oops, and that should be green. The atomic mass will be on the bottom. Okay, so it'll be like right here. And then the atomic number will either be in the right-hand corner or it'll be in the left-hand corner. There won't be two of them, just so you know. It won't be mentioned twice, but it'll be in the left-hand corner or the right-hand corner. It just depends. But again, the biggest difference is that, for the most part, atomic mass is in a decimal, it's a fraction, whereas the atomic number is the whole number. So again, when you see whole number, think atomic number. When you see decimal, think atomic mass. Okay. And it's also just if it should make sense. Think of it this way. If you're working with an average mass, and we're talking about things that are crazy, crazy small, but that are measured with crazy, crazy accurate and precise equipment, you're going to have a decent range of numbers. And at the same time, you're going to have a decent range of numbers for each kind of isotope, each type of each element. It's going to vary a decent amount. So an average is, for the most part, when you work with averages, you get decimals, right? So whereas atomic number, it's exactly this. It's the number of protons. Okay, it's the number of protons. Okay. So let's keep going. Okay, so what's mass number? I'm so glad that you asked. Now, mass number, and this is the thing. It's funny. because I don't have a terrible amount of students confusing mass number and atomic number. I have more students confuse atomic number with atomic mass. They just forget what mass number is. And hopefully this year I can get you guys to remember what it is. But what the mass number is, which sometimes you can't find, or I should say a lot of times is not provided on a periodic table, unless it's like an interactive online one, which I'll show you at the end of the video here. But the mass number is the combination of the number of protons plus the number of neutrons. Okay, so again, it's the number of protons plus the number of neutrons. And that's a pretty big distinction. And again, it's not last year that I had kids that that got it confused. Oh my goodness, sorry. It's not that I had kids confuse mass number with atomic number. They just forgot about it. So do not forget about mass number. Because again, this all ties into how we represent particular isotopes, particular elements, using a complete chemical symbol, which we'll practice at the end here, and that you'll practice after these notes. Okay. So mass number, again, this is just the number of protons plus the number of neutrons. Okay. So for instance, as an example, aluminum's mass number is 27. Okay. It's 27. So let's figure that out real quick. Well, how do we know, or let's just say, let's say we're given 27. Well, what does that exactly mean? So if aluminum's mass number is 27, okay, well, we don't exactly know how that's divided, I guess, as of yet, but let's try to figure that out. So if, that's why it's super dirty. That's why my stylus is not working very well. But anyway, but let's say this. Okay, and then I got to scroll up. Sorry. Let's see. So what we do know, okay, we know that its mass number is 27, and we also know that the atomic number is 13, which means that aluminum has 13 protons. Well, if the mass number is the number of protons plus the number of neutrons, well, we can just do this. We can say, well, we can figure out which is which. So we can say, 27 is equal to, it'll be sorry, I'm blanking here, number of protons plus the number of neutrons. And we already have the number of, oh my goodness, stylus. Maybe I got to replace it. We've got the number of protons. We need the number, we would like to know what the number of neutrons is. So it's just all that's going to be, just simple algebra. It'll be 27, and it'll be minus 13. And then we find out that it has, oh my goodness, that aluminum has 14 neutrons. Okay, so why did I do this and how did I get here? Remember, this was given, okay? Now you'll be doing some practice where you've got to find what the mass number of aluminum is, okay, or a particular isotope. You'll have to figure that out using a complete chemical symbol with knowing its charge, give or take, I guess. Yeah. So anyway, but how do we get here? So again, we got here because we were given the mass number, and we want to know what that mass number is made of. And what I did is that I said, well, the mass number is 27. Okay, so the mass number is 27. And I know that the mass number is equal to the number of protons plus the number of neutrons. Okay, I don't know why I spelled that out. That must mean that it's 27 is equal to 13 plus, we'll say just x, because we don't know what our number of neutrons is, and it's just simple algebra. We subtract 13 from each side, so it gets rid of it there. Then it's 27 minus 13, and we're left with 14. So that tells me that there's 14 neutrons. Now again, this is going to be important to know, because this kind of information is going to change our complete chemical symbols, and it's going to change the type of isotope that we have. Okay. And then another example, calcium's mass number is 40. Okay. And you'd find that you can use the same information there. Is that 40 minus, in this case, 20. So that means that calcium, or the most abundant calcium in the world, has 20 protons and 20 neutrons. Okay, so I hope you're still with me so far, because again, this should still be somewhat, familiar. Uh, so, okay, ion. So what's an ion? What does it have to do with anything? Well, we're going to be working a lot with ions throughout the year. And pretty much what ions are, it's an atom that has gained or lost either one electron or more electrons, and thus giving this particular element a charge. So you could imagine that. And remember, your electrons are negatively charged. That's, I guess, that's not why electron, other than the fact that it carries, a decent chunk of energy surrounding the, and surrounds the nucleus of a of an element, or sorry, of an atom. Okay. Electron has a negative charge, where proton has a positive charge, neutron has a neutral charge. It has no charge. Okay. So when you lose an atom, you can imagine that when you lose one, that means you're losing a negative charge. So instead of becoming either going from a neutrally charged element, you may become a positive element, or maybe even, that is my first one. My first example here. So think of it this way: losing electrons gives a positive charge. Okay. And this is how we write them. So let's say sodium is losing or lost one electron. That changes the charge to a positive 1. Okay. Now we got to stop and talk about this, because this is part of your worksheet, part of the activity. So if sodium here lost an electron, what we say here is that one electron has changed. Okay, so we put the number first, and then we put the charge. So we put, okay, that means that we have a single electron that's changed, and it's for the positive, meaning that it's gone, it's left, which I know doesn't sound like a positive, but remember, electron is negatively charged, and if we lose a negatively charged thing, we now have typically a positively charged thing. Okay. So again, the order is this, and we'll practice this. So the order is like this. When we are describing an ion, when we are describing the charge of a particular element, we write the element's chemical symbol. We then display the number of electrons affected, and then we say how those electrons were affected. Plus sign is when you lose electrons, whereas the negative sign is when you gain electrons. Okay. And that's what the next point is going to be about, what it's going to detail, sorry. So here's a good example. So gaining electrons gives a negative charge, because again, electrons are negatively charged. So if you gain them, you're going to have a more negatively charged thing, in this case, an atom. So if oxygen were to gain 2 electrons, this is how we write it. So we would write O. We would write O because that is oxygen's chemical symbol. And remember, we're going to write the number of electrons. Oh, and it's also important, or I'll mention this after saying this. So we've got our chemical symbol. We've got the number of electrons changed or affected, and then we're going to say how they're affected. And I almost did the opposite thing. And how they're affected, which in this case we gained 2 electrons, so it's 2 negative. Okay. And what I interrupted myself with is that the position that we place these on the chemical symbol is very, very specific. So we place when we're listing ions, we place the number and the symbol in the top right-hand corner of our chemical symbol, almost like it's a superscript, because we want to keep it small but big enough in order to see and not in the way of anything else. Okay. So this is important. So if I see this, just so you know, if I see this, that's wrong, okay? If I see this, okay, that's wrong, okay? And also, if I see this, which I know I'm going to see a whole lot of, okay, that is wrong. Ew. again, we talk about, these are two, right? We talk first about the chemical, we talk about the element, then the number of electrons affected, and then how they were affected. Did we gain or lose here? How many were gained or lost? What element are we dealing with? Okay. Those aren't P's, I guess. Those are just showing you what I'm talking about and where I'm talking about. So that's an isotope. Or sorry, that's an ion. Sorry, that's an ion. All right, so now finally we get to ask that question, Mr. Sheeline, what's an isotope? Or a better question, is mayonnaise an instrument? Whichever question, whatever works, man. But in this case, an isotope is an atom of the same element. This is the same number, so it means it has the same number of protons that has a different number of neutrons. No, I did not stutter. It has a different number of neutrons. It has a different number of neutrons, but the same amount of protons. Okay? Think of it this way. If you change the number of protons, you're fundamentally changing the how would I say that? You are changing the electronegative balance of an atom, because you're taking a positively charged thing out of it. So you are making it somewhat unstable for that brief period of time until it corrects itself by either getting rid of or gaining electrons, and maybe booting a neutron or two, maybe. But for the most part, because it's positively charged, and if you get rid of one or add one, you're changing the entire, you're changing the structure of that element, thus changing it to a whole new element. Okay. So, but isotopes, they can, there are different isotopes that can have a different number of neutrons. It can have, a couple few. It can maybe have one or two few. It could have, a couple more. It just depends upon the element. It depends upon the environment it's in. It depends upon its half-life, which is something we get into down the road. It all depends. Okay. But what you need to know now is that an isotope is an atom of the same element, same number of protons that have different numbers of neutrons and therefore different mass numbers. Okay, let's see. So as an example, don't highlight. So as an example, when we are, we're talking not an example, but we're talking about how we write them. So when we're writing the type of isotope in its written form, okay, what we do is that we what I've got right here, we have the element's name, like a written out name. Okay, so this is what I'm looking at right here. This is how we, without using a complete chemical symbol, we can do this. We have a written isotope form of telling people what we're working with. So we'll have the element's name dash mass number. Okay. So for instance, carbon 12 here. So carbon 12. So remember, isotopes have the same number of protons, just different number of neutrons. So we'd write out carbon dash 12. Okay. Same thing with carbon 14. We'd write carbon dash 14. Okay. And this is important information that tells us something. So remember, and what I was getting to in a bit earlier, wow, time is weird. Carbon 12 has 6 protons. Okay, well, how do we know it has 6 protons? Well, we can look up at the periodic table and we'd see there's carbon. Oh, and the whole number, it's a 6. So that means that because its atomic number is 6, that means that carbon has 6 protons, which it does. Now, when it's carbon 12, though, okay, and because the 12 is the mass number at the end, remember how we find the mass number? Remember the mass number? We would go back. Mass number is just equal to the number of protons plus the number of neutrons. So if we know the number of protons and we know the mass number, we can then know how many neutrons we have. Or the other way around, if we know the number of protons we have and the number of neutrons that we have, we can then find the mass number. And then we can write it out like we do here. Okay. I know this is a whole lot, and trust me, like if this is overwhelming for you now, good, okay, because things are going to, as we progress through the year, things are going to obviously get more complicated, and so if we're it's best now to get used to that so we know to prepare for the future. Okay. So that's, again, so up here, this is how we write out the written form of an isotope. Now the complete chemical symbol. So now we should have all the bits and pieces that we need to make a complete chemical symbol. Okay, so a complete chemical symbol includes the mass number, the atomic number, the chemical symbol of an element, and its charge. Okay. And I, for the most part, have walked through each of them. So we know how to find the mass number. We know where to find the atomic number. We know where to find the chemical symbol. And we know how to show its charge if it has one. Okay? Okay. Now, these are arranged in a specific way, though. So let's take a look at how we do that. And this is how we do this. Okay, let me get rid of this. Insert time when you sing, this is how we do it. Anyway, so this is exactly what we do right here. So we have the mass number to the left, like in superscript. We have atomic number over here to the left in subscript. We have our chemical symbol in like normal large font. And then we have our charge in the top right-hand corner, like superscript. Okay, so let's do an example here. Let's say we still don't get it. Okay, let's look at a complete chemical symbol for a chlorine ion. So a chlorine ion. Okay, now this isn't enough information to know which ion because there are different numbers of. There can be, but for the most part, all you have to know for now is that because chlorine. No, you don't even have to know that. Never mind. I'm saying too much. Wow. I don't want to confuse you more than I probably already am. Well, let's just do this. So a complete chemical symbol for chlorine. Okay, so I'm going to look at my periodic table, and I'm going to see that chlorine has a chemical symbol of Cl. Okay, so I'm going to underline these with particular colors, and then I'm going to write these in the same color. Okay, so I've got the chemical symbol. Now the mass number. Well, the mass number I may not know, or let's see. Well, that's right, because we just don't have enough information. But let's say, how to do this? Let's just say that this mass number, I'm just going to give it to you, is 36. Okay. And then the atomic number here, again, now this one we can definitely find. If we look up at the periodic table, or we look into a periodic table, we can see that chlorine in the periodic table, there's a 17, and we've got its atomic number. Now, in this case, I'm just going to tell you that the charge here, well, this ion, it has gained an electron. Now we get into why it gains an electron later on. Okay, but for right now, I'm just going to say, well, it gained one electron. So, okay, so I've got my chemical symbol. I'm going to tell how many electrons were affected, and now I'm going to tell how it was affected. We gained one. Okay, and then you have your complete chemical symbol. Let's see, find a, yay. Maybe that isn't good. Maybe our chemical symbol is going Super Saiyan. I don't know, man. But anyway, it's correct. This is how you label it. Okay, we've got our 36 over 17, our chemical symbol, and then the 1 minus. Okay, so this tells me, as a reader, that this chlorine is an ion. And this tells me that this, because I can see the 1 negative, this tells me that this chlorine is a particular isotope, that this looks like to be. If I were to tell you what this is, let's see, what color? I pretty much use all the colors. Oh, I could use this one. So if I wanted to write out this particular isotope, this is going to be chlorine. Let's see. Well, my mass number is 36. Oh, or sorry, that's it. It'd be just that. Sorry, I forgot. Just your mass number. Okay, and we know that from up here. Oh, I gotta do this. We know that from up here, remember? So right here. So like this, we put the mass number at the end. So this specifically is chlorine 36. Okay. And here, I'll even write that. Look at that. Oh, come on. Okay. So cool. Yay. So that's the type of isotope. It's a chlorine 36. Okay. And this is how we then write the complete chemical formula, or sorry, chemical symbol, which is what you're going to be practicing in this packet that you're going to be working on in just a bit. The last thing that I've got to cover is more or less just review. So lastly, just remember, here are the atom components reviewed and table. So remember, and maybe some of this isn't review. So for instance, like symbols, maybe you didn't know the symbols, maybe you didn't know the locations, or you forgot the locations, maybe you didn't know about the mass. Okay, so protons here. So this is a symbol. This is P with a plus up at the top, like a superscript. It's found within the nucleus and has a charge of +1. It's a positive charge, and it's roughly about 1 AMU. And we get into what AMUs are down the road. Okay, we won't worry about them too much here, but we worry about them closer to November when we get into I'll just say that. We worry about it down the road. Okay. We have neutrons, and then neutrons here. This is the symbol right here. This is found inside the nucleus. It doesn't have a charge, but it also has a mass of about 1. And then you've got your electron here. The electron, here's its symbol. This is outside the nucleus in the electron cloud. Its charge is negative, and it is pretty close to not having any mass at all. Okay, it does have mass. It's super duper tiny, so we just don't really worry about it. But anyway, okay, and then actually the last thing that I'm going to go and just show you is a really neat website. Now, I don't expect you guys to know the website in and out as of yet. That's something that we'll continually work on as the semester and as the year progresses. We'll work with. But all you need to know is that this thing does exist. This place does exist. Okay. Oh, the thing didn't come out. Uh-oh. Okay, sorry. And that place is called ptable.com. Now, ptable.com is pretty cool. And not because I'm super duper just I don't know, weird about it, but it's when you need to know certain properties of a particular element in the periodic table, it's really, really helpful if you know what to look for and if you know what you're supposed to be doing. So what's really cool about it is that it's a super interactive website showing you all of these elements, showing you the chemical symbol, plus it'll show you the atomic number, it'll show you the atomic mass, it'll show you the I think, let's see, it doesn't tell you. But anyway, what you need to know for right now is it shows you right now, I'm losing my train of thought here, sorry. It shows you the atomic number, the atomic mass, and also the written form of its name, which is pretty cool. And you can, let's see, does it still do this? I guess it doesn't do this. What it used to do, maybe this thing on the side is what it does now. It used to take you to give you like a Wikipedia. Oh, it still does. Oh my god. I don't know what I did, but okay. But anyway, something I can play with because they've really changed this up, which is really cool. But anyway, it's just a cool website to use as a reference. Again, don't freak yourself out over this. I'm not going to expect you guys to know how to use this website, but it is a really cool resource. And just to show you real quick the isotopes, this is really neat. Let's see if this still does it. If I click on beryllium here, oh my god, it still does it. It's even better than it used to be. I know you're probably seeing this and it's really laggy. It's not on my end. It's really cool. It shows you all the different isotopes that each element is found on the planet. really, really neat. Again, you don't need to know these. You don't need to know how to use it. It's just a really, really cool resource. Okay. So anyway, all right, guys, that is the end of the lecture. I know this kind of ran a little long, but this is the lecture. So now what I want you to do is I want you to take what you learned here in this particular lecture, and now I want you to apply it to that packet. So what you're going to be doing is you're going to be telling me the charge. You're going to be telling me or the charge of a particular ion. You're going to be telling me the number of protons an element may have, the number of protons it may have or neutrons it may have, the mass number with the provided information. And you are also going to practice on how to make the chemical symbols, the complete chemical symbol. So it's imperative that you listen to this. It's imperative that you understand this. If you do not, make sure you go back to this video. Go back to the points where I show you how to do things, and I will timestamp these in here for you. So please, if you didn't notice I timestamped them, look in the description because I timestamped them so you can go back and see how you make a complete chemical symbol. So you can go back and see how you get the atomic mass, how you get the mass number, okay? And I'm super drived up right now. It's 5:53 p.m. here on Monday. Oh my God, why am I not home right now? Why am I still at the school? I don't know. God bless everybody. I will see you when I see you. If you have any questions, let me know. If you want to subscribe to this to know when I upload videos, cool, I guess. That's kind of neat because then you want to know when I'm posting stuff. So, but anyway, if you have any questions, please let me know. If not, I'll see you in the next one, guys.